Welcome to my capstone project presentation. My name is Ines Brooks. I am excited to walk you through my project title, Enhancing SOC Alert Prioritization Using Machine Learning. This project is the result of everything I have learned in a data analytics program, particularly how to use supervised machine learning and explainable AI to solve real-world cybersecurity challenges. The purpose of this presentation is to explain the problem I'm solving, the work completed so far, and the key lessons I have learned along the way. You will also see how this project connects directly to my career goals in cyber defense and data leadership, especially my aspiration to become a chief data officer. Let's begin with the project scope. The scope of this project is centered around addressing one of the most pressing challenges in cybersecurity operations: alert fatigue. Every day, security operations centers (SOCs) are overwhelmed with thousands of alerts. Many of these alerts are false alarms or lack critical context, making it difficult for analysts to respond efficiently. My project seeks to use machine learning to classify these alerts into three categories: true positive, benign positive, and false positive. True positives are real threats that require immediate attention. Benign positives might look suspicious but turn out to be harmless or less critical, while false positives are completely irrelevant and false alarms. By training a model to distinguish between these types of alerts, SOCs can better prioritize their response efforts, saving both time and resources. This scope includes data selection, data preparation, model training, evaluation, and interpretation. It also includes using explainable AI to ensure transparency. Next, I will walk you through the specific problem this project addresses. Now, let's dive into the problem itself. SOC teams rely on tools that generate thousands of alerts every day. However, not all alerts are created equal. In fact, a significant portion of these alerts are either redundant or misleading. When analysts spend their time investigating false alarms, it increases the likelihood that they might miss a genuine threat. This problem is further complicated by the complexity and the volume of modern attacks. Adversaries now use advanced persistent threats (APTS) that often bypass traditional detection methods. Manual triage methods are simply not scalable. My project addresses this issue by automating a part of alert triage process through machine learning. The central research question is, can a supervised machine learning model effectively classify alerts to assist analysts in prioritizing their response in real time? The model must not only be accurate but also interpretable so SOC can trust the prediction it makes. Now, let's explore why solving this problem is so important. This issue is critically important for several reasons. First, as organizations increase their digital footprints, the volume of cyber threats also increases. False alarms not only overwhelm analysts, but also raise operational costs and lead to alert fatigue, which can cause burnout and decreased performance. Rapid detection and triage of security incidents are essential to maintaining a security environment. Metrics like mean time to detect (MTDD) and mean time to response (MTTR) are used to measure the effectiveness of security operations. Reducing these metrics through automated and intelligent systems improves organizational resilience. From a strategic standpoint, this work aligns with my goal of becoming a chief data officer. The CDO role increasingly involves making data-driven solutions, managing AI systems, and ensuring regulatory compliance. This project provides real-world experience in developing explainable and responsible AI solutions that serve business and security goals consecutively. Next, I will describe the dataset that powers this analysis. Let's talk about the dataset. I use the Microsoft Security Incident Prediction dataset, which is available on Kaggle. This dataset contains over 13 million alerts generated in simulated enterprise environments. Each alert includes metadata such as the alert ID, timestamp, user and device information, and a target variable called incident grade. Incident grade includes three categories: true positive, benign positive, and false positive. The dataset includes 45 features, many of which are categorical or timestamp based. After initial inspection, I found that the dataset has a lot of missing values and duplicated records. So, I cleaned and prepared the data accordingly. By dropping the columns that have a lot of missing value and removing a small portion of the records. After that duplicated records has been dropped from the analysis, and we kept only one instance from each. I also created new features such as hour, day, and weekend from the given timestamp features to help identify time-based patterns in the alert in a more meaningful way. These transformations were crucial in preparing the data for modeling and visual exploration. With the data prepared, let's look at the tools and the methods used to build the model. For the tools and the methods, I use Python together with Google Colab as the primary development environment. I use Pandas and NumPy for data cleaning and transformation, and Seaborn and Matplotlib for visualization. The machine learning models to be used are logistic regression, decision tree, and random forest, each offering different strengths in interpretability and performance. Different performance metrics are going to be used to check the model's usage, such as precision, recall, F1 score. Finally, to make the methods explainable and build user trust, sharp values will be employed to highlight which features are more valuable for the model. This is particularly important in SOC environments where transparency and accountability are essential. Let's now explore some of the visual insights generated during the data exploration. Let's look at some key visual insights from my exploratory data analysis. First, I plotted the distribution of the target variable incident grade. The distribution of the alert IDs has been checked to see what are the frequent alerts in the system. At the end, the nearly temporary features weekend has been explored to check if there is any relationship between the week of the day and alert frequencies or not. Let's take a closer look at the first visualization, the class distribution. This chart shows how alerts in the dataset are distributed across the three target classes: true positive, benign positive, and false positive. As you can see, there is a significant class imbalance. The majority of alerts are labeled as benign positive, followed by a smaller number of false positive, and then fewer true positive alerts. This imbalance presents a major challenge for machine learning because most algorithms will naturally learn toward predicting the dominant class. To address this, I use strategies like class weighting and focus more on evaluation metrics like recall and F1 score rather than just accuracy. This visualization was one of the first and clearest signs that the model would need tuning to avoid bias toward the benign class. Next, let's examine the distribution of alert IDs. This visualization gives us a closer look at the distribution of alert IDs in the dataset. As you can see, the vast majority of alerts are clustered at the lower end of the ID range. That means a small number of alert types are happening over and over again, possibly triggered by routine system activity or repetitive events like scheduled scans or low-risk detections. Next, we look at how alert patterns differ between weekdays and weekends. This chart compares alert types between weekdays and weekends. What stands out is that there is a much wider variety of alert categories on weekdays. During weekends, we see a reduction in both the number and diversity of alerts, which is expected since fewer users and the system are active. This trend suggests that data weekday versus weekend might influence the likelihood that an alert is real or false. As a result, I included a binary feature, weekend, in the final model to help it better assess the likelihood of true versus false positives based on the day of the week. Now, let's review what has been completed so far in the project. To date, I have made significant progress. I cleaned the data by handling the missing values and removing the duplicated record from the data. I extracted more features from the timestamp data to create more useful feature from. Class distribution has been analyzed and identified that benign positive was the dominant class. This confirmed the need for addressing behavior before starting the model training process. I also conducted a literature review to align my work with best practices. For instance, the study by Kalatoki and others used LSTM models and explainable AI to classify alerts and demonstrated the importance of model transparency. This validation reinforced the direction of my own project, particularly in integrating SHARP for explainability and choosing appropriate evaluation metrics. Let's reflect on some key lessons learned during this process. As I worked through the data and the initial analysis, several lessons emerged. First, I realized how critical data cleaning is, not just for quality, but also for model performance. The removal of nulls, duplicates, and irrelevant columns helped reduce noise and computational complexity. Second, I gained a deeper understanding of how class imbalance can distort model accuracy. If you don't address it, the model might just predict the majority class and still look accurate. So, dealing with unbalanced datasets requires careful attention. Third, through my research, I learned how valuable explainability is. Security professionals won't trust a black box model. SHARP analysis will be used to help me identify which features were more influential in each prediction, making the model's decision transparent and interpretable. Finally, I learned that research alignment matters. The work by Kalatoki and others helped validate my design choices, getting some ideas on what steps should be taken along the way. I will now outline the next steps in the project lifecycle. As I move into the final stages of this project, my next steps are clearly defined. I will begin by training and evaluating three baseline models: logistic regression, decision tree, random forest, using the clean dataset. Each model will be assessed using different metrics such as per class recall, precision, micro, and weighted F1 scores and confusing matrices. I will also apply hyperparameter tuning to improve model performance and address overfitting. Because of the class imbalance, I will use resampling strategies like SMART and class weighting during training. Once the best performing model is identified, I will use SHARP to produce features attribution plots that help explain why certain predictions were made. This will allow me to make data-driven recommendations for SOC operations. Lastly, I will finalize the writing report, prepare visuals, and conduct a review of ethics and privacy considerations to ensure the model is fair, transparent, and secure for deployment in real-world environments. Now, I like to acknowledge the key sources that supported this work. References used include research paper on explainable AI, performance metrics, industry definitions of the CDO role, and Microsoft datasets. These sources informed every aspect of this project, from methodology to evaluation strategy. Now that I have covered the key sources that guided my methodology and the decisions, I will move to the final slide to conclude this presentation. Thank you so much for your time and attention. This project has been an incredible learning experience and a big step toward my career goals. I will be happy to answer any question you might have. Have a great day.